John Watt, and welcome to Ever Wondered. Achieving a sustainable society may be the biggest challenge of an entire generation, and the generation of power is the biggest part of that challenge.
It seems that our love affair with oil is ending in tears. Many suggest that we are nearing the peak of global oil production, and from there it will be a short and painful trip down. We have already made good use of natural energy sources, and almost 3/4 of our electricity comes from renewable sources, the majority from hydro. But it is this small chunk of new renewables that we are looking to expand to take the place of fossil fuels and meet our rising energy needs. This week, I'm talking to the Kiwi scientists that are researching these alternatives. First, I'm off to Scion Research in Rotorua. Trevor Stufferidge is looking into some new uses for one of our oldest fuels.
What we're doing is we're taking wood and we're breaking it down into sugar, and we're turning the sugar into biofuels.
Wood is part of the new generation of biofuels. The first generation used oils, sugars and starches.
If you look at cornstarch-based biofuels, then for every litre of oil you use to drive the tractor, etc., you get the equivalent of 1.4 litres of biofuel back. So pretty close to neutral. But with wood material-based biofuels, you get about 4 litres of bioethanol back for 1 litre of fossil fuels.
The first generation fuels use food crops, but the disadvantage is that this can lead to price rises and food shortages.
The advantages of our technology is we're targeting material that isn't for food, so that's trees. So in that case, we don't get into food competition issues.
New forests can be grown on land that is currently of very little value.
We think there's more than enough land to double the forest estate in New Zealand. Under that scenario, we could replace 65% of all the fossil fuels in this country.
Scion are currently refining their methods, using a small-scale pilot plant to take the wood through the first stage of processing. The scientist charged with perfecting their techniques is Ian Suckling.
Right, Ian, so what have we got here?
So these are chips from radiata pine. They're the starting material for our process.
Radiata pine is used because it grows quickly in New Zealand conditions. But these chips have to be broken down further with some pretty serious kit called a refiner motor.
What's actually inside it is over refiner plates here.
Alright.
And you can see here the chips come in the centre.
Yeah.
And then they exit out through there and they appear out of there as pulp.
Oh, so the teeth get smaller and smaller.
So the chips get smaller and smaller, broken up, just like you would in a grinder. So you might grind up meat.
Now that the mechanical breakdown is complete, the chemical breakdown can begin.
We get the pulp out of the mill that comes down, and that's a sample of it there. We then dilute it with water and we get a mixture like this material here. Then we add the enzyme.
An enzyme is a protein that speeds up chemical reactions. In this case, Ian's goal is to break the long chains of cellulose and hemicellulose down into simple sugars. The solution is also heated and gently agitated to give the chemical reaction some extra energy.
As a result of it comes out of that, you get out a solution containing the simple sugars and then a residue that's left behind.
Ian then checks the results of this process by testing for sugar.
So what kind of yields are we getting?
So we're getting up to almost 70% there, which we're quite encouraged with, and the higher that we can do, the better.
The sugars can then be fermented into biofuels.
We can make ethanol or biofuels. Can we do it cheaply enough? That's the challenge.
Trevor's fuel currently costs $1.64 per litre, whereas, not including the tax we pay at the pump, a litre of 91 costs around the $1 mark. But as Trevor and Ian refine their processes, their fuel will get cheaper, while the cost of petrol is only heading one way.
We believe the break-even for our fuel is about $90 a barrel. So once oil reaches $90 a barrel, it makes sense to consider biofuels.
The oil price today is around $75 and will surely continue to rise as our global reserves run dry.
It's a race against time to find a suitable energy replacement for oil. And what better replacement than, well, oil?
Nick Gerritsen is making crude oil from one of the most abundant plants on Earth, algae.
What people have forgotten is that, the crude oil that we pull out of deserts was actually largely algae originally, except it's taken millions of years or tens of millions of years. What we've done is that we've turned it into a real-time event.
The site Nick chose to find his algae is a sewage works. Here the algae thrive in the nutritious waste of Blenheim's 30,000 residents.
The algae spores settle in the water, photosynthesize, they eat the nutrients, and so their role here really is a clean-up role.
So where do you plug in?
We plug into the discharge point where the algae's done its thing, so rather than the water going out into the ocean, it can go into our gear.
A huge innovation in this system is to plug directly into existing infrastructure so that the minimum of new engineering is required. Nick also wanted the technology to be transportable so it could be used at any wastewater processing plant in the world.
What we did, we gave our staff the challenge saying, okay, well, here's a pond, here's a container, you have to work out a way of taking that green algae out of that water, and all the gear has to fit in there. So they sort of had a year and a half of like blowing stuff up.
So this is the final product?
Yeah, when you can sort of see it's got sort of oily characteristics. That's
Yeah,
like.
looks quite appetizing.
So once we've taken this out of that, we end up with cleaner water as well.
5.3 billion litres of water from this plant alone currently flows into Cook Strait.
So by us taking the algae out, we release that 5.3 billion litres of water so it can potentially be used for irrigation purposes.
This cleaner water can, of course, be sold, offsetting the cost of producing Nick's green crude. The algae from Blenheim now heads to Nelson. Paul Dorrington is a scientist who's speeding up the process of making crude oil by a few million years.
Here is the algae paste, so you can get a whiff of that.
It's kind of like sushi and burnt here.
Yeah, it's very marine. So mix it all around, get it into a nice, even consistency before we feed it through into the rest of the process.
Paul is secretive about his techniques, but they mimic the natural process of turning algae into crude oil by adding temperature and pressure. But the key step is to add catalysts. These speed up the chemical reactions.
So here is where we're collecting the biocrude out of the process. And what we can see in here, we have a kind of viscous material.
Yeah, it's quite solid, eh?
It's quite solid, absolutely, yeah. This has a whole range of different materials in it.
Crude oil can be used in countless applications, from fuel to pharmaceuticals, and Paul's green crude is no different. His latest accomplishment is to create the first ever aviation fuel from wild algae.
It's straight out of nature and into the jet engine.
Into the jet engine, yeah.
Awesome.
We were only into this by not even 2 years, and we were already getting calls from Boeing. And so for a small New Zealand innovation company, it's actually relatively surreal to walk through some of the largest, most strategically important doors in the world.
These doors were opened by an incredibly economical process that taps into existing infrastructure and makes everything it produces more valuable.
If we include the water remediation revenue, we have a per barrel price for crude oil, which is between 77 US and 80 US a barrel.
That is only a little more expensive than today's rising oil price. So Aquaflow's science looks like it will have a bright future.
There's no reason why this technology couldn't be applied ubiquitously around the world in open oxidation pond scenarios. That is exciting.
I'm here at Industrial Research Limited, where there's a company that's leading the world in the cutting-edge field of high-temperature superconductors.
Bob Buckley is the manager of the team conducting this revolutionary science.
Superconductors are materials which allow you to conduct electricity with unmeasurably low electrical loss.
Normal power lines use copper wire and lose between 7 and 9% of the energy as heat due to resistance. Because superconductors have no resistance, none of the energy is lost and the wire doesn't heat up. This means you can put loads of current through it without it melting.
So this is a good example here of the advantage of superconducting cables over copper. So you can see this bar here is very much larger than this small superconducting cable. Both these objects will carry 2,000 amps.
So this thin little cable carries as much electricity as that.
That's right.
That's amazing.
But this benefit does come at a cost.
You've got this great advantage of unmeasurably low resistance, but the penalty is it has to be run at a low temperature.
Minus 163 degrees Celsius to be precise. This might seem an extreme temperature, but the previous generation of superconductors operated at minus 269 degrees, almost absolute zero. The expense of the refrigeration engineering required to keep the cables cold means it is only economical when a lot of power is involved.
One immediate application is bringing power into very dense city centres. New York City already has a few superconducting cables now.
Bob's company led the world by finding this superconducting material. However, it is a ceramic.
This is like your cups and saucers. If you drop them on the floor, they break. You've got to turn that into a wire. That's the biggest challenge, and that's why this technology has taken 20 years to just start to enter the marketplace.
Engineering genius Rod Badcock was the man given the seemingly impossible task of turning this material into usable cables.
It's actually quite a complex composite structure here. Only 1% of that piece there is actually superconductor. You start with 60 microns of stainless steel. On that you put about a micron of superconductor.
So you've got all that electricity going through 1/1,000,000th of a metre of superconductor material.
Absolutely. The analogy is, what we have here is 2 cream crackers with a smear of butter and a bit of jam, and the jam is our superconductor, if you like, but brittle. And we want to cut and shape that without breaking the cracker and without smearing the jam out. So that's actually really hard to do. And it took a bit of development effort, and this is what we ended up with here. So this is an automatic process now.
This is your machine, there's your name.
Yeah.
So built and designed by you, awesome.
Yeah, so it was developed here in New Zealand.
Oh, can we fire it up?
We certainly can.
Rod's machine cuts and shapes the tape so it can be made into a cable.
Internationally, other groups have tried to do an automated process like this, but nobody else has really been able to maintain the superconducting properties. We can produce hundreds of metres in a go.
So you can make hundreds of metres of this high-value stuff a day?
We can make hundreds of metres of this high-value stuff in just over an hour.
That's pretty impressive.
The most obvious use for a cable is plain old power transmission, but that's only the tip of the superconducting iceberg. Possibly the application with the greatest potential is the wonderful world of magnets.
Without magnets, you'd be back in the Stone Age, because most of the systems that we use are powered by electricity, which is generated with some form of magnetism.
This is because magnetism and electricity generation are inextricably linked. A magnet has 2 poles, north and south. These poles are attracted to each other, so a magnetic field passes between them. Now let's look at a conducting material. It conducts electricity by moving electrons, but when there is no current, the electrons are relatively static. If we bring a magnet towards the conductor, its magnetic field causes the electrons to move, creating a current. Then things get even more interesting. This current creates a magnetic field of its own.
Here we've got a sample of the superconductor wire, but it's not in its superconducting state yet. To do that, I've got to cool it to around minus 200 degrees Celsius, which I'm going to do with liquid nitrogen.
The colder the superconductor becomes, the greater the conductivity, and the stronger the magnetic field it can generate.
So to test this, we'll add a magnet. And it levitates.
So the superconductor has become strongly magnetic and created a force large enough to defy gravity.
I could play with this for hours.
So using superconductors in electricity generation can make things smaller.
Making things smaller also enables things to be done that simply weren't possible before. So if you take wind generators, for example, maximum power you can get is about 5 megawatts, because they become physically too large and too heavy to have a generator high up on a tower. So by making them smaller, you can now go to something like 10 megawatts. So there'll be less wind turbines, but generating much more power.
The discoveries of Industrial Research Limited are already worth tens of millions of dollars to the New Zealand economy, with that expected to rise to hundreds of millions in the near future.
In New Zealand, we can do internationally competitive research, and that's happening now and opening up significant commercial opportunities for New Zealand and New Zealanders.
The fastest growing form of power generation in New Zealand is geothermal.
I've come to find out about a project that's hoping to solve New Zealand's energy problems by harnessing the awesome forces below our feet.
Greg Bignell from the Institute for Geological and Nuclear Sciences uses his geology skills to hunt down the superheated fluid required for power generation.
We're exceedingly lucky that New Zealand is blessed with these geothermal resources. It's having a huge impact on the country. We're up to 15% of electricity is now being generated from geothermal resources.
The first geothermal plant in the country was Waiareke Power Station.
So you can hear that awesome rumbling. You can even feel it vibrate. I mean, there's a lot of power in this.
What you can hear is the mixture of steam and liquid racing down the pipelines, spinning around and separating the liquid phase from the steam phase.
Geothermal power works by extracting extremely hot fluid from deep below the Earth's surface. The steam from this is used to drive a turbine before being injected back into the ground to heat up and begin the process again. But in the new generation of geothermal plants, the hot fluid can also be used to create even more electricity at a binary plant.
So what happens in the binary plant?
The binary plant is a big heat exchanger. The separated water heats the working organic fluid isopentane, which boils at about 35, 36 degrees. It vaporizes and goes through a turbine and generates electricity as well.
So you're getting more bang for your buck.
Absolutely, that's what we want.
Awesome.
The geothermal industry in New Zealand has developed the low-hanging fruit. If we drill deeper and find hotter resources with greater energy, the potential is there to virtually run the country on geothermal resources.
The low-hanging fruit were picked at around a depth of 3 kilometres, but the drilling is now expected to go as deep as 6 kilometres.
These are the types of rigs that we'll be drilling hotter and deeper in the future.
Right, I mean, it looks like a huge project. It's an expensive process.
We're looking at $30 million just to drill the hole. It's a very expensive process, and that's why we have to get the science right and have to get the engineering right.
In order to persuade the power companies to make the investment, Greg does a huge amount of research that can build up models of what lies beneath. One tool that helps him paint this picture is the fluid that is trapped within tiny pieces of crystal. These crystals were formed in geothermal fluid deep within the Earth and carried to the surface.
The fluid that's trapped in there is a sample of the fluid that was moving through the rock at the time that crystal was formed.
By analysing this fluid, Greg can tell precisely how hot it is kilometres below. To do this, he heats up the sample and keeps an eye trained on the tiny bubbles within the fluid.
At the point that bubble disappears, that was the temperature at which the fluid was trapped in this crystal. 260.5 degrees.
Is that quite hot?
In general terms, if it's greater than 250 or 60 degrees,
that's the money.
That's the money.
It is science like this that will ensure the continued expansion of geothermal power generation in New Zealand.
Personally, it's great to feel that you're using your science and actually contributing something to the country.
Geothermal is only one method of extracting energy from water.
If we could effectively harness the immense power of our oceans, we'd solve all of our energy problems. So I'm off to meet some guys that are giving it a go.
Alistair Gardner is developing technology that generates electricity from ocean waves.
The engineering challenge is quite significant. It's got to be able to interact with the wave energy and absorb it in an efficient manner. And the forces that you get involved are difficult to put up with in an engineered structure.
So Alistair is working on a design that works with rather than against the awesome forces of the sea.
The key thing we're trying to do is extract energy from two different directions, if you like. We call it the multi-mode technique.
The inspiration for this technique is the motion of energy within a wave itself. This is circular, so the energy moves in all directions. The team began their testing with a tiny model.
Right, Alistair, this is a scale model of the device. What information do you get from this?
Well, we can learn an awful lot before we have to scale up, so it costs a lot more money to build bigger devices.
Right.
What we're doing here is separating the energy flows into two separate motions, a heave motion and a pitch motion. The land, can we get some heave motion first?
So this is the up and down.
This is the up and down motion.
So this is what traditional wave generators will get.
So we're separating them out so as you can understand the principle. And
The idea is to use as much of the complex energy a wave produces as possible to move the triangular float up and down. This motion creates electricity by driving electrical generators in the device's two turrets.
What about this one?
Now we can create slowly a slight movement, and you'll see how the hole is starting to move backwards and forwards.
Yeah.
So
Because the device is anchored, it creates a pendulum motion. This increases the extension angle between the hull and the float. So this mode of movement also drives the generator.
The trick is to work the device such that those two motions combine so that we maximise the extension about that pivot point.
Right, so you get a lot of force on that pivot.
Yeah, a lot of force, and therefore we can extract more power.
Once Alistair and his team were confident with their design, they began scaling up.
Right, so this is the wave machine. Can you tell me about it, Alistair?
Well, this one is what we call our quarter scale device.
Oh, this is the quarter of what the thing's going to be.
Yeah, that's right.
This thing's huge, though. So how much energy can this one produce?
Well, this one will produce around about 2 kilowatts peak, which is not a lot. I mean, it's enough to maybe power 2 houses. We are talking about going to a half-scale device, getting 10 times the power that we get out of this one.
Right.
And a full-scale device will be 10 times the power again. So we're talking about
So
100 times.
More.
Yeah. So our full-scale device will have round about, we're estimating at the moment, 200 kilowatts of peak power. So that's we think that's a level that starts to look commercial.
So it's like 200, 300 houses, that kind of thing.
Yeah. And obviously, as the technology is developed, we'll scale it up further and maybe get up to around about 1 megawatt per device.
Today, the quarter-scale device is being relaunched for another mission, gathering information to help Alistair build the next model.
I and my colleagues spent quite a lot of time looking at the sea and recognising the potential of it, and dream about achieving the impossible, although realistically we think that it'll be probably 5 years from now before we'll see sort of individual devices in the water. And it took wind technology 30 years to get where it is today and become a viable commercial energy generating form, and wave energy will expect to follow the same pathway.
New Zealand is clearly blessed with natural sources of power, and our scientists are working hard so that the dream of having an energy mix that is 100% renewable may soon become a reality.